Okay, so in the previous class, we have discussed the differences between complex exponentials in continuous time and discrete time. So we have some important conclusions. Let me revise. We have this signal and this signal. This is xt, this is xn in discrete time. Or you can also compare them with their sinusoidal counterparts, omega naught n plus phi, and this you can take as a cos omega t plus phi omega naught t. Okay, so there were some important differences that we have explored. So first difference was that this is periodic with a time period of 2 pi by omega naught. This may or may not be periodic depending upon whether 2 pi by omega naught is the ratio of two integers or not. If it is a ratio of two integers, in that case your n becomes the time period. Okay, second important difference was it has an infinite frequency range. For this signal, the frequency range is finite and that is limited to a band of 2 pi only. Okay, it means all the signals between minus pi to pi, they will be unique, and if you go beyond a band of 2 pi, the signal will start repeating. So it is not necessary that you choose a band of minus pi to pi, any 2 pi band. It may be 2 pi to 4 pi, 3 pi to 5 pi. Within that band, the signals themselves are different. So in the last class, I have given one example where we have seen that when you start from the zero frequency in the discrete time, where you get a constant signal, as you go on increasing the frequencies at pi, you are getting the maximum rate of oscillations. Then between pi to 2 pi, the frequency starts decreasing, and at 2 pi you again get a frequency which is equal to omega is equal to 0. Okay, but if you see the frequencies between pi and 2 pi, they are nothing but the negative frequencies which are same as minus pi to pi, minus pi to 0. Okay, means if I take a frequency cos of omega suppose 1n, where omega 1 is lying between 0 and pi, and then I take another signal with the frequency of omega 2, where omega 2 is 2 pi minus omega. It was a cos of omega 2 n, and omega 2 n is a cos of 2 pi minus omega 1 n. So if you see this, it is nothing but a cos of 2 pi n minus omega n. So cos of 2 pi minus theta, it is cos of theta. Okay, so it will become your a cos of minus omega 1n. Okay, it means now see for cos function, no doubt, because this signal cos of minus theta is cos theta, so cos omega 1 and cos omega, this will be also cos omega 1. But if you take a sinusoidal function, it will become cos of sine of minus omega 1, that will become minus sine of omega 1n. Okay, otherwise see for the cosine function, even this signal, and suppose if you have a signal here, maybe I take it as pi by 2, cos pi by 2 and cos of 3 pi by 2, they are same, although the frequency difference between them is not 2 pi. Okay, but if you see 3 pi by 2, this is nothing but 2 pi minus pi by 2. Okay, so what we're basically getting here is a negative frequency, and since it is a cosine function, For the cosine function, your positive and the negative frequencies, they give you the same signal. But if you take a sinusoidal function in the form of sine function, you will get different frequencies. Okay, so this I think I need to clarify because you may get confused in this point. Okay, and then the third uh, part that we have discussed, the difference between them is that as you increase the frequency from 0 to pi, you are getting the highest rate of oscillations at pi. And then as you increase further frequencies, the rate of oscillation decreases, and at 2 pi it becomes same at omega is equal to 0. So low frequency signals are near 0 and pi. High frequency signals, they are close to pi or mod odd multiples of pi, whereas this is not the case here. So as you increase the frequency, your rate of oscillation, it continuously increases continuous time. Okay, this is what we have discussed. Now I will just take one more example on this to further elaborate it. I take three signals. One is, suppose your cos of uh, maybe pi by 6n. One is cos of 8 pi by 31n, and another is cos of n by 6. Okay, all are discrete time signals. So for this signal, if you find their time periods, you have to first express omega by 2 pi. Okay, so omega in this case is pi by 6, so it will become pi by 6 into 1 by 2 pi. It will become 1 by 12. This is periodic signal with a period of 12 samples. What about this? Omega by 2 pi will be equal to, omega in this case is 8 pi by 31 multiplied with 1 by 2 pi, so you will get 4 by 31. Again, the ratio of two integers. This is also periodic. 31 is the time period, here 12 is the time period. And for this signal, omega by 2 pi will be, omega is 1 by 6, so 1 by 6 into 1 by 2 pi, you will get 1 by 12 pi. So this is not in the form of k by n, so this is not periodic. This signal is not periodic. Okay, now see, suppose you can, if it is a continuous time signal, it might be like this, cos of pi by 6t. This would have been cos of pi by 31t, and this must be cos of t by 6. I have taken the same signals with the same frequencies in continuous time. Okay, now in the continuous time, this is always periodic. What is the time period? Time period for this is 2 pi by omega. Omega is pi by 6, it will be 12. Time period for this signal, it will be t is equal to 2 pi by omega. Omega is 8 pi by 31, so it will become 31 upon 8 pi. Okay, so for this signal, what is the time period? It will become 31 by 4. Okay, pi will get cancelled 4, you will get 31 by 4. And for this signal, cos t by 6, what is your time period? It is 2 pi by omega naught, that is 1 by 6. 2 pi by r into 1 by 6, you will get pi by 3. Okay, now you can say that these discrete signals, they can be simply obtained from the continuous time signals if you just take your t is equal to n. Okay, in all the signals, If I replace t is equal to n, it means my sampling time is 1 second. Okay, I can convert cos pi 6 by t to cos pi by 6 n. Now since n is integer, it is 0, 1, 2, it means t is 1, 2, 3, 4 only. In between you have no samples. Okay, no fractional values. But in the continuous time, all the signals are periodic. If you sample it in the discrete time, all the signals, they are not periodic. In fact, they have different time periods. See, if you look at the first case, cos t by 6n and cos pi by 6n, both are periodic and the time period is 12. Okay, if the time period is 12, it means in 1 second you are getting 12 cycles. Okay, so let us suppose I take this signal. Okay, this is one cycle, 2, 3, 4, 5, 6, 7, 8, 9, then 10, 11, and 12. And this time period is your 1 second. This is what is cos of pi by 60. Okay, plus 1 to minus 1, phase is 0. Now, why these two signals have the same time periods? Because when you sample it, you are sampling at t is equal to 1, at t is equal to 2, at t is equal to 3. So when you reach at t is equal to 12, which is a time period of continuous time signal, at that time you will exactly get a sample also in the analog domain. Okay, because t is equal to 12 and n is equal to 12, you are getting the same sample. So that is why they will repeat in the same time period. Whatever is the time period of continuous time signal, the same is the time period of discrete time signal. If you look at the second case, the continuous time signal has a time period of 31 by 4, but discrete signal has a time period of 31. So why it is so? Because if this signal has a time period of 31 by 4, but you are sampling it at a time of 1 second, that is you are taking only integer values, so you will not get a sample at 31 by 4 in discrete. Okay, so when it will repeat, when it will complete its 4 cycles, means if I multiply this with 4, I will get 31. So in the first period, you will not getting a sample at that point, integer value. In the second cycle, also not. Third cycle, also not. In the fourth cycle, when this continuous time signal will repeat 4 times, you will get a sample at 31 at that time. So after 31 samples, this is going to be repeated. And in this case, since in the continuous time, your time period is pi by 3, which is a rational number. In the discrete time, when you sample at t is equal to n, you are not getting a sample exactly at this point for any time period. Okay, because since n is integer and this is a rational number, you will not get. It means even if the signal is periodic in continuous time, when you sample it, it will not be periodic in discrete times. I mean the samples will never repeat. Okay, so now another important thing we will discuss, that is when you convert a continuous time signal into a discrete time signal using the sampling, how we should choose a sampling rate. Okay, so you have a continuous signal xt. When you sample it, it becomes a discrete signal x of n. And how we sample it, we take its signal at 0, then at t, then at 2t, then at 3t, then at 4t, and so on. This is the sample signal. Okay, now the problem is we have to see whether sampling is a invertible process or not. It means whether we can recover this continuous time signal back from its samples or not. The answer is yes, but we have to satisfy some criteria of how to choose this sampling time. In general, you can say that sampling is not a invertible system. That means you cannot always get this continuous signal back from its samples. But if you satisfy some criteria on the selection of this t, capital T, which is sampling time, obviously you can recover the original signal. Okay, so we will start again from the continuous time sinusoid a cos omega t plus phi. So sampling, it means sampling of this signal. What it means, if I sample it, what means that I am using, now for this function I am just taking the values at t 0, then capital T, then 2t. It means t I have to replace with n times capital T, where capital T is my sampling time, and the inverse of sampling time is called as sampling frequency, 1 by fs. Okay, 1 by t is fs. So if t is equal to nt and n is an integer, if I replace this equation in xt, if I replace small t with capital N into capital T, I will get its sample signal, because now we're getting sample only at 0, then at t, then 2t, and 3t. It means my equation will become xn is equal to a cos of omega. In place of t, it will become nt and plus phi. This is the sample signal. Now if you compare this signal with its original equation, that is a cos of omega n plus phi, what you can get is that you can see that the relation between this omega, that is angular frequency in the analog and in the digital frequency, is nothing but you will get this omega will become omega t. Okay, or in terms of f, if you want to write, it will become 2 pi small f is equal to 2 pi capital F into 1 by fs. So your f is nothing but f by fs. So these are two important relations. How you map basically the analog frequencies into the digital frequencies. Okay, because when the signal is in the continuous time, it has a infinite bandwidth. Okay, when you sample it, it becomes discrete, which has a finite bandwidth. Now when you sample it, so sampling simply means what? It is a mapping of the frequencies from continuous time to discrete time, and this mapping should be unique or one-to-one. It means the infinite range of frequencies should be mapped only to a finite band of frequencies. Okay, so each frequency in the continuous time, this should be mapped to only one frequency in the discrete domain. So when you choose the sampling rate or the sampling frequency, we have to make sure that the signal that you get after sampling, its frequency omega must be between this band. Okay, if the frequency is within this band, then that signal will be unique. If the frequency of the signals goes beyond pi, you will get Alice components. Okay, Alice means you will get in that case one more frequency which is similar to that frequency within this band only. So in that case, it is not possible to say whether that sampled signal is recovered from which signals. Or you can say that in that case, in continuous time, you can have two signals which if you sample at the same rate, you are getting the same discrete signal. So there is an ambiguity there. Okay, so in order to avoid this situation, we have to assure that our frequency of the discrete signal after sampling should be between omega should be between 0 and pi only. Okay, and how you can assure that? Omega is your omega t. Okay, or f is your fs, or in terms of f, you can say that this frequency f should be between 1 by 2 to minus 1 by 2 to 0. Okay, I am taking about the positive frequencies only. Otherwise, you can take it from minus pi to less than omega less than pi also, no issues. Okay, but the basic concept that is you have to choose a sampling rate in such a way so that the discrete signal that you obtain, its frequency must be less than pi. This is you have to assure. Omega should be less or equal to pi, or in fact mod of omega, whether it is a positive or negative frequency. And how you can assure that? Or you can say that f should be less than equal to 1 by 2. Now see, if you see the relation between the continuous and the discrete frequencies, this is the relation. Capital F is the frequency of the continuous signal in hertz. Fs is the sampling rate in hertz. What signal you get after sampling, the frequency of the signal is f by fs. It means if I have a continuous time signal of 5 hertz frequency, and if I sample it at suppose 20 hertz, this is my sampling rate frequency. This is the frequency. What would be the frequency of discrete signal? It is nothing but 50 by 20, 1 by 4. Okay. So what should be the fs, maximum value of fs for a given f, so that f is less than 1 by 2. So that fs should be greater than or equal to 2f. Okay. Because when sampling frequency is just equal to 2f, your f will become 1 by 2 or omega will become pi. You will get the maximum frequency. If you choose fs higher than 2f, this f will always be less than 1 by 2. Okay, so this is the criteria now. So the criteria for sampling rate is that you have to choose a sampling frequency which is greater or equal to twice of the maximum frequency in the signal. This is called a sampling theorem. And when you simply choose your fs is equal to 2f, just equal to twice of the maximum frequency, this is what is called as Nyquist rate. So fs is equal to 2f means you are sampling the signal at Nyquist rate. So if you satisfy this criteria, you will see that the discrete signal that you obtain after sampling, its frequency is always less than pi. Okay, it means there are no alias frequencies. You are getting a unique signal. But if it is less than 2f, in that case you will get alias components. Okay, so let me take one example on this. Suppose I take two frequencies, two signals, one with a frequency of suppose 1 hertz and another signal with a frequency of 4 hertz. Okay, and I sample both the signals at a frequency of 5 hertz. Okay, or just take me this as 4 hertz. One is the frequency of 1 hertz, another frequency of 5 hertz. The sampling frequency is 4 hertz. Okay, both the signals they are sampled at this sampling frequency. 1 hertz frequency means you can take a signal like this, suppose cos of 2 pi into ft, f is 1, so cos of 2 pi t. This is 1 hertz frequency signal. 5 hertz frequency signal means cos of 2 pi into f, that is 5 t. So it is cos of 10 pi t. Okay, sampling frequency is 4 hertz. So if a sample both signals at 4 hertz, what is the discrete signal after sampling? It will be simply cos of f by fs. So I have to simply divide 2 pi with 4 and replace t with n. So it will become cos of pi by 2n. And similarly here, cos of 10 pi by 4n. It will become cos of 5 pi by 2n. Okay, these are the discrete signals that you will get after sampling. And you can say that this signal is nothing but, I can write it as 2 pi n plus pi by 2n, become 5 pi by 2n, and cos 2 pi n plus theta is again cos theta. So you will again get cos of pi by 2n. So what it means? Both the signals are same in discrete time. So two different frequencies in continuous time, 1 Hz and 5 Hz. If you sample both the frequencies at 4 Hz sampling frequency, the discrete signal will be exactly same. So you cannot differentiate whether this signal is obtained from this or whether signal is obtained from this. So you can reconstruct it. And why this problem is coming? Because see, if you see this frequency has a 1 Hz sampling is frequency, the minimum sampling frequency for this should be 2 Hz. But since we have taken 4 Hz, so you are getting a discrete signal where the frequency is pi by 2, it is less than pi. So it is unique, no doubt. But this signal has a frequency of 5 Hz. So the minimum sampling rate for this should have been 10 Hz. And since we are choosing a sampling rate which is 4 Hz, which is less than the Nyquist rate, so you are getting a signal, and for this signal we have another signal which is already present in the band of 0 to pi. Okay, so if the samples are given to you, so from these samples you can get so many signals. But if you have assured that the sampling rate for this is greater than the Nyquist rate, in that case you will just get only one signal, and that is this signal of 1 Hz. Okay, so what it means is that if you plot it maybe suppose 5 Hz frequency, what is the meaning of 5 Hz frequency and 1 Hz frequency? 5 Hz means in 1 second we are getting 5 cycles. Okay, so I take one cycle, 2 cycle, 3 cycle, 4, and then 5. This is 1 second time period. This is 5 Hz frequency. Now another frequency we have 4 Hz, 1 Hz. It means in 1 second you are getting 1 cycle. Okay, so this is 1 will be 0.5. This will be somehow here 0.5. Okay, so 1 Hz frequency will be, it means that 0.5 1 Hz frequency, if you plot it, this is 1 Hz, this is 1 second. Okay, so 0, this is 0.5. At 0.5 will get the maximum in the negative direction. So if you plot both the signals on the same graph, and in between there's you will get some zero crossing point, then this is another zero crossing point, and then maxima. Okay, so it should be something like this. This is 1 Hz frequency, black one, and this is your 5 Hz frequency. Now if you sample both the signal at 4 Hz, it means the sampling time is 1 by 4, that is 0.25 seconds. So where I will get samples, that since the output is same, it means the samples that you will get, they are nothing but at the points where the signals they cross each other. Okay, if the signals cross each other, at that time basically you are taking the samples. So as a result, the discrete signal that you obtain, it is same for both. Okay, this is what is called as aliasing. Aliasing distortion means two signals, when they are sampled at the same sampling frequency, you are getting the same discrete signal. And why this problem is happening? Because we have not chosen a proper sampling rate for one signal. Okay, if we choose a proper sampling rate which is higher than the Nyquist rate, this problem will never come. Okay, it means if you have a sampling rate of fs, the signal that input signal which you are sampling, its maximum frequency should be limited than fs by 2. Okay, so if in a system we are using a 100 hertz sampling frequency, the signal that must pass through the system, its maximum frequency must be limited to 50 hertz only. Okay, otherwise if it is beyond that, you can have aliasing distortion, right? And one more important thing is that when sometimes you encounter when you sample exactly at the Nyquist rate. Okay, uh, let us suppose you take two signals or three signals. One signal has is a frequency of 1 hertz, that is 2 pi t. Another signal, maybe a sine signal, with a frequency of 5 hertz, that is it will be 10 pi t. And another signal with a frequency of suppose uh, 20 hertz. Okay, so it will be 40 pi t. This is my input signal, analog signal, which is basically now a mixture of three different frequencies. Okay, how should I choose the sampling rate for this signal? This must be greater than twice of the maximum frequency in the signal. Okay, so when the signal itself is a linear combination of different frequencies, you have to see what is the maximum frequency in that. Okay, so for this frequency is 1 hertz, this is 5 hertz, this is 20 hertz. It means the sampling frequency for this should be now 40 hertz. Okay, the maximum frequency you have to see it is 20 hertz, so twice of that it is 40 hertz sampling rate. So for most of the signals, like say if you have a speech signal, the maximum frequency contained in a voice signal is around 3 kilohertz. Okay, so if you are digitizing the speech signal or the voice signal, you should choose a sampling rate of minimum 6 kilohertz. Okay, similarly for any other signal, if you say ECG signal, if you use digital filter design for ECG processing, so ECG has a maximum frequency of around 100 hertz. So 200 hertz is the minimum sampling rate for that, and so on. Okay. Now, if you sample this signal at just Nyquist state, that is fs is equal to 40 hertz, what will be my output signal or discrete signal? Or just I will take this as sine function. Okay. This is suppose sine, not cos. I want to make some important conclusion, that's why I have chosen this. So discrete signal will be cos of 2 pi by 40 n f by fs plus sine of 10 pi by 40 n plus sine of 40 pi by 40 n, or you can say it is cos of uh, pi by 20 n plus sine of pi by 4 n plus sine of pi n. Okay, this is the discrete signal that you obtain after sampling. Now if you see to this signal sine of pi n, this is nothing but 0, because it is sine 0, then sine pi, then sine 2 pi, 3 pi, everything is 0. And why it is happening? Because I am sampling this signal at its Nyquist frequency. Okay, 20 hertz is the frequency in the signal. I am sampling it at 40 hertz. What actually I am getting is that when you sample it, the samples that you are taking, they are nothing but coming at the zero crossing points. So as a result, you get only zeros output. This means the information related to this signal is now completely lost in the discrete signal. Okay, you're just getting zeros. See, this is like this, and this is for any signal. Suppose if you have frequency of 1 hertz, Okay, sine function. 1 hertz frequency means this is 1 second. And let us suppose I choose a sampling rate for this, or a sampling frequency for this Nyquist frequency, that is 2 hertz. 2 hertz sampling frequency means what is sampling time? It is 0.5 seconds. So this is 0, zero point 0.5 is here, then 1. Then you are getting next sample at 1.5. That is again 0. Then 2. Again 0. It means the samples that you are basically taking, you are taking the samples just at the zero crossing points. Okay. As a result, the discrete signal that you get is nothing but a sequence of zeros. So how you can recover this signal back from samples? Not possible. Okay, because the signal information is totally lost after sampling. So what I try to conclude is that it is generally not advisable to sample a signal at its Nyquist rate. Okay, we should always choose a sampling frequency which is greater than twice of the maximum frequency. A simple solution to avoid this problem is this. Okay, if you choose a sampling frequency which is just equal to twice of the maximum frequency, you may get a situation like this where you are sampling the signal only at the zero crossing points. As a result, this signal information will totally be lost. Okay, so this is how we should choose the sampling time for any given signal. If it is a linear combination of more than one frequencies, you have to see what is the maximum frequency in the signal, and then based on that maximum frequency you have to choose your sampling frequency, but it should be greater than twice of its maximum frequency to avoid any loss of information. Okay.